All right, so I got all the streaming already enabled. So YouTube is already starting to record, and Discord has the usual live stream. So people are just starting to stream, kind of come in at this point. So I do want to share with you, in case you haven't watched the video or check out the general chat, that I made syntax highlighting rules for Vim, VI improved. So potentially this is useful because potentially we can. Oh, before we do that, let me answer a question from a student in the class. Uh, so So I am teaching CISP 310 in the summer as well. There won't be any modifications to the curriculum due to uh, the time. So it's going to be compressed. The summer session is only has about 8 weeks, so I'm compressing 16 weeks worth of material into about 8 weeks of real time to go over. So instead of meeting twice a week, which we are doing at this point, it'll be meeting 4 times a week. So each week will be just be doubling the amount of material that will be gone over. So that's how the summer session is going to go. Um, and this is the first time ever that I actually teach in the summer. And this is also the first time ever, as far as I know, that CISP 310 got offered in the summer. But because the time frame is really just 50% of the usual 16-week semester, so it's really just compressed accordingly. So we end up with 4 days of classes instead of 2 days of classes per week. So I hope that answered the question from that particular student. Um, yes. So let's go ahead, and I still got about 2 minutes or so, and we'll see it today too because I'm gonna use NVim or NeoVim today, and just kind of use today's lecture as a testing and also a debugging session for the syntax highlighting specifications as well. So that's going to be fun. If anyone wants to use NeoVim or just regular Vim and want to understand how to integrate all of this stuff into NeoVim, let me know and I can do a quick demonstration, or not so much demonstration, but show you guys where you can download N or NeoVim and how to install it and what you need to tweak to make use of the tool that I have developed just this morning. So are there any questions before we start today's lecture, which is a continuation of the discussion of structures? Last time we looked at a linked list and we performed summation over the linked list, and what we'll do today is we're going to write a subroutine to do that. Okay, we can write a subroutine to search for something in the linked list. We can write one to append something to the end of the linked list. So there are a few things we can do today, but all of those things are going to illustrate how we can handle the concept of structures and pointers and recursion in assembly language programming. All right, we got about a minute to go. All right. That is a good question. I think NeoVim is going to work natively in Windows, so you don't even need SigWin to do that. Because if you go to the NeoVim website, okay, so let me go back to the actual site over here. So if anyone looks for NeoVim, okay, which is new Neo VI improved, okay, so we can definitely see how VI has come along, from the, I would say, maybe from the maybe 70s, 80s or so. Okay, so if you go to NeoVim's website, you can go to their download link. Well, they don't have a download link, but they have an install now link. So if you click on that, it will bring you to GitHub. And then within GitHub, you can download different packages depending on which operating system you are using. So if you use Windows, okay, you can use Choco to install. You can use Scoop to install. I don't use Windows much, so these ways of distributing and installing packages is new to me. Um, so for those of you who know how to use Windows, you can probably tell me more about uh, these two different ways of installing packages in Windows. They also have pre-built archives, so I'm assuming this really is just a zip file. You just have to unzip it, and then whatever folder it unzips into has the executable. So you don't even need to actually install it. So you have three ways to install NeoVim in Windows, and then there are also various ways to install it in Linux. In Mac OS X, there are two, and then in Linux, obviously, depends on which distribution you use. I personally use Debian, which is already in the main distribution itself. So that's up to you guys, whether you want to install it and on what platform you want to install, and also based on that platform, what options you want to use to install it. All right, so time is 5:31, so almost 32. So let's go ahead and get started. All right, so we'll go ahead and start with a program which is more or less a continuation of the program from before, from this Tuesday. So I'm hoping all of you had a chance to kind of read, annotate, and analyze and understand the program that we talked about on Tuesday. Because what we'll do today is kind of based on that. Okay, so we'll go ahead and do something related to what we just did on the other day. All right. So let's go ahead and look at a program where we create a linked list out of an array. Okay, so this is basically what we do. What we're doing is we're creating a linked list of free nodes. Okay, so we'll say allocate.c. So I'm going to write the entire program in C first. All right, so we have pound include stdint.h, standard integer.h, and then we have a structure definition, and we can use something that is very similar if not exactly the same as last time. So we have uint8 underscore t, which is a value, and then we have struct node pointer, and this is pointing to the next node in a linked list. So we're still looking at a linear linked list and not a tree or anything that's complicated like that. And then this time we'll use an array. So to initialize this whole thing, we're going to use an array. We'll say struct node. So whether the array needs to be a global variable or a local variable, let's make it a local variable because I think this makes it kind of somewhat more interesting and somewhat more realistic. So we have main, and then we have struct node, and this is the array. Okay, so we have a node array, and we'll give it a certain number of elements. And let's go ahead and properly do this and use a macro to define the length of the array. Okay, so we'll say number of nodes, and let's just say that I have to be careful here because I have to make sure the assembly version also has enough room to implement this. So we'll just say 4 or 3 is fine. Okay, let's just make it 3. So this is num nodes right there. Okay, so the first thing we want to do is to create a linked list of nodes that are available, and then we'll go ahead and try to make use of the what we call a free list. So this is a list of nodes that are available. So this is where things start to get a little bit interesting, because we have a pointer. Okay, and we call it p-free because it is a pointer to free nodes. Okay, nodes that are available, and initially everything is available. So we want to create a linked list based on this. And to do this, let's use a subroutine to attach a linked list, to attach a node to the end of a linked list. Let me see which way is better. We can attach it at the head or the beginning. Okay, so that's fine. We'll make it a void function, and we'll say list, and to insert something at the very beginning is to shift. Okay, so we say shift, and then we have to give it two things. One is the list itself, and the other next one is a node. So let's just name the parameters first. Okay, so the first one is a list, and the second one is a node, because what we are trying to do is to attach the node to the beginning of that list. Okay, now now that we have to think about the types of these two, let's think about this a little bit more. Okay, so let's start with node. Node is going to be a structure node something. Okay, but the thing is, even though we can pass structures by value in C and C++, it is not a very good idea to do that. And the reason is it is very inefficient. You're copying the entire node onto the stack, and in this particular case, we are not actually changing it. Okay, so here's a question. Hugh is asking, is the stream on YouTube live? Let me check. I thought I clicked the button. Yes, it should be live. It doesn't seem to be. Hmm. So when passing, okay, so Joshua is asking the question. When passing by value, we are creating a copy. Yes. So in any programming language, when you pass something by value, you're basically making a copy of the original thing, and then you push it on the stack. That's how we pass something by value in all programming languages, not just C and C++. But certain programming languages cannot pass objects by value, like Java cannot do it. Okay, so the question is, do I mean inefficient because the size needs to pass by value? So it's both. Okay, so the size is a part of it, and the second part has to do with actual execution time, because you have to copy the entire structure byte by byte. Now, depending on the size of the structure, obviously the overhead can vary. But in this case, node is relatively small. But if node has a huge payload, which means the value part is big, then it is very inefficient. Ramsey has a question. Copying pointers is bad. Shallow copies. Okay, so we are referring to terms that are usually used in a scripting language. When we make a copy of a data structure in, let's say, JavaScript or Java, typically we're performing what we call a shallow copy, which means we're just duplicating either the pointer or the reference in the new thing that we are creating. So it's not a deep copy as opposed to shallow versus deep, because a deep copy basically is going to allocate new objects along the way, so that the new versus the clone versus the original, they are entirely different. Okay, you can make changes to one and it has no impact whatsoever to the other one. But with a shallow copy, they are still linked because they're sharing references. So if you change whatever the reference is referring to, then both copies will get the change, and that's why shallow copies are. You have to be careful with shallow copies, even though they're very efficient in when we need to perform certain operations. So so that's a good point. Okay, Ramsey did bring up a very good point. But in C and C++, it's a whole different thing, because there's no language ability to make copies other than the assignment statement. So the kind of copies we can make is totally dependent on the type. Okay, so getting back to here, okay, if I want to attach a node to the beginning of a list, I really don't want to pass the node by value. I want to pass it by reference. Now, since I'm not using C++, there's no way to pass something by reference. The ampersand does not work to specify passing by reference, so I can only pass it by pointer. So now we have to move on to the list. What exactly is a list? A list is really a pointer to a node to begin with. But since list shift is going to change the list itself, so now we are looking at something that is now a double pointer. So we are looking at a struct node double asterisk pp list. Okay, it's pp because it is a pointer to a node, or actually I should say just p list because a list by itself is a pointer to a struct node. Okay, so let's just take a look here and find out what we are trying. Well, okay, I will implement the code first, and then we'll use GDB to find out exactly what this code is doing. So this is one thing about the topics that we are in at this point is uh, some of the concepts is difficult to understand, even if it is in C. But the nice thing about these concepts when specified in C, and well, you can look at this as C++ too, which is a superset of C for the most part, is we can actually run the code, okay? Run the code in GDB, set up breakpoints, and then find out what is going on in GDB when the program is still written in C. Because then we will start to understand, how the program, how the data structure is put together, and then at that point, we can then translate the code into assembly because then only then we'll have the ability to test the code to see whether it works correctly or not. Okay. All right. So the code that I'm going to put in here, so typically you want to include some kind of error checking code. So basically we say if plist is null, okay. So a short form to say that is not plist. Then we don't want to do anything. Okay, if we want to throw in an exception, we cannot do it in regular C, but you can do it in C++ or Java. So we are not going to deal with this case. So the other way to specify this is if plist is non-null, then we got something to do. And we also want to make sure that p node is non-null either. Okay, so p node really should be non-null. So we also want p node to be non-null because otherwise you have no node specified to attach to the beginning of a list, and that doesn't make sense. Okay. Well, the only time it makes sense is the only time that would make sense is when you're trying to initialize a list. Okay, so you're basically saying this is an empty list to begin with. So let's allow that case to happen. So we'll just make sure that plist is empty. All right. So eventually, the one thing that we want to do is to say whatever plist is pointing to. So can someone tell me what is the type of what plist is pointing to? In other words, if I just look at line 15 at this point, okay, what is that? What is the type of that expression? Asterisk plist. What is the type of that expression? Can someone tell me about it? You can type it. You can also just say it out loud in the voice channel. But what is the type of that expression on line 15 right now? It's a pointer to a node. Very good. Okay, good job. It is a pointer to a node. Okay, so that means if the left-hand side of an assignment is a pointer to a node, the right-hand side should be that as well. And guess what? P node is already of the right type, and it is the proper thing to do. But I cannot just do this, because what if plist is already pointing to a node? Then we have to attach whatever plist was pointing to the new nodes next. Okay, so I'm not sure whether that concept is conveyed or not. Okay, because we're dealing with a linked list. Plist is pointing to the beginning of the entire list. So if it is not null, if whatever plist is pointing to is if it is not null, we have to adjust that thing so that it points to how should I put it? We have to adjust what p node is pointing the next member of whatever p node is pointing to, so that it points to whatever the list has as the first item first. Then we can adjust the head of the list to be the new node that we wanted to point to. Okay. It is best to also include some kind of explanation here. Okay. So we basically are saying that plist or whatever plist is pointing to yes, So so RJ is correct. We have to assign the p next member of p node. We have to change it first before we change p list. So graphically, I know this is not exactly very graphical, but whatever p list is pointing to is a pointer itself, and that pointer is potentially pointing to a node already. So we'll just call this node uh, node x. Okay, our parameter p node is potentially pointing to another node. We'll call it node y. Okay. This is one scenario, by the way. It's not the only scenario because it is possible that the list is currently empty, so that star p list is actually pointing to null, in which case the new node is the first node. Okay, but this is a kind of a more general case. So after the operation happens, this is what we want to what it want to end up as. We want p list, or what we want star p list to point to the new node, which is currently pointed to by p node. So we want this to be node y, but we want node y itself to point to the node that was already in the list to begin with, which is node x. So this is before, and this is after. Okay, so is that okay? Does everybody understand what we are trying to accomplish here? Kind of more graphically. RJ is typing. I'm gonna wait a little bit here. So p list must point to node y, and node y's p next member should point to node x. That is correct. Okay. So now that we got the picture, okay, we'll basically say, well, is p list pointing to a node already? Okay, so we'll say if p list star p list is pointing to something already, then we have a little bit of adjustment to make. Well, let's see. We don't even need to do that. We can just say p node its next is going to be whatever p list star p list is pointing to. So this line on line 22 is what makes node y point to node x. Okay, line 22 is accomplishing that. So now the only thing left for us to do is to adjust p list star p list. So instead of having star p list to point to node x, now we want it to point to node y, and that is accomplished by line 23. So do we have any questions about these two lines of code? RJ is typing. I'm going to wait a little bit. Does the order matter in C and also in assembly? Okay, so let's answer those questions. The answer is yes, it does matter, because if you reverse the order, then you would have destroyed or modified. Let me think about this. If you change p list first, yeah, it would matter, because p list is we need line 22 to use the original p list, or whatever p list is pointing to, and then we want line 23 to change that. So it does matter, because p list is being changed. Now the interesting part that we should notice is p node itself is not being changed in any way, because on line 22 p node is not being changed. It is a member the p node is pointing to. The structure p is the member p next of the structure the p node to point to, that is being changed. P node itself is not being changed. On line 23, p node is also not getting changed. So from the perspective of p node, it doesn't make any difference whether we perform line 22 or line 23 first. But from the perspective of whatever p list is pointing to, it makes a difference, because on line 22 we need to use the original pointer the plist is pointing to, and then on line 23 we are changing it to point to the new thing. So that's why the order is important between line 22 and line 23. All right, excellent. All right, so what we'll do is we are going to give it a try. Okay, so we'll go ahead and make a loop to do the initialization, and we can do it in main itself. Okay, I'm not going to pull it out of main as a subroutine. So we'll go ahead and do this all in main. So to do this, I will need a index variable uint8 underscore ti, because I have to go through the entire array. There are several ways to go through the array too. You can use a pointer to go through an array. You can use an integer or an index to go through an array. So we'll go ahead and actually use the other way, because to do it this way needs multiplication, which we cannot conveniently do. So we're going to use the other method to do it. So we say struct node typo. So this is going to be, it's really just a node that we're pointing to. So we just call pn in this case, p pointed to a node. And before the loop, we say pn is node array. And then we now say as long as pn is less than node array plus num nodes, okay, do the following. And make sure that we increment p node at the very end, okay? And then for each iteration, pn is pointing to a specific node inside the node array. So we will pass that to list shift in order to add that particular element to our list. So that means we need another local variable here, which is our list. Okay. So our list is a pointer itself, and we call this free list, okay, because it is a list of nodes that are available. And initially it is initialized to 0. Okay. Or if you do not like it like this, and we want to do it completely separately, we can always say free list is null over here. So now we want to pass an element of node array to the subroutine so that it can attach that particular element at the beginning of our free list. So the call to do this is list shift, and then we have to specify our free list here. Okay, so I'm going to do it wrong, so don't copy anything. I'm just going to I'm going to do it wrong first, and then we'll go ahead and fix it, because I want to explain what is going on, in this particular call. Okay, and then the second thing is whatever pn is pointing to. Okay, so intuitively this seems to make sense. Okay, we are looking at whatever pn is pointing to and say, hey, this is the node in the array, and I want to attach that to the free list. Okay, that seems to make sense, right? But the types are all wrong. Okay, so let's go ahead and compile this program first. Okay, we'll let the compiler try to figure out what is wrong with this code, and then we'll come back and fix it. So we use GCC, and I don't think we even need warn all, but it's okay to do that. And we can see that, let's just focus on the error. Okay, the error is on line 25. It complains about incompatible type for argument 2 of list shift. This is what we are supplying as the argument is actually a struct node, but what the parameter is expecting is a pointer to a struct node. Okay, so that's one thing that is wrong. But if you look at the warning, it's kind of interesting. It only complains about this as a warning. On the same line, it's complaining about the first argument too, because the first argument is of the type struct node pointer, but the parameter is expecting struct node pointer pointer. Okay, so this is a this is where having a compiler makes a big difference, because in terms of assembly language, a pointer is a pointer. Okay, it really is just in the toy processor. all it is just 8 bits. Okay, in a 64-bit architecture, it is just a pointer which is 64 bits. But what it points to, there's no information about what it points to when you write a program in assembly. But when you write a program in C or C++ or any strongly typed programming language, the compiler is keeping track of, okay, I know this is a pointer. Okay, it's itself is only 64-bit wide, and it points to a location in the entire memory space. But the compiler also knows what it is pointing to. Okay, that byte that it points to, oh, this one is pointing to the first byte of a structure. This one over here is pointing to the first byte of a 64-bit integer, and that one over there, it is pointing to the first byte of a 64-bit pointer. Okay, so the compiler can keep track of all of these things so that when you are not utilizing pointers correctly, the compiler has a chance to complain about it. So now let's go back and change the program. Okay, we'll go ahead and fix this program so that it compiles and works correctly. So what we need to do is to specify ampersand in both cases, because we are passing the address of free list, which by itself is a pointer to a struct node. So that's why the argument itself actually has a type of a pointer to a struct node. That is what the first argument is about. The second one also needs an ampersand, okay, because we are not actually passing the structure by value to the subroutine. We're passing the address of the node that is pointed to by pn, to the subroutine. But when you look at this expression over here, okay, when you look at ampersand, open paren, star pn, close paren, yeah, exactly. RJ is exactly right. The ampersand and the asterisk cancels out. So we are really just passing pn to the subroutine. So this is the correct way to do it. Okay. So what we'll do is let's go ahead and compile, and then we'll use GDB to go through this program, just so that we have a chance to figure out what is going on with this code. Okay, still complains because p3 is not used. That's okay. Okay, it is not going to be optimized out. All it is complaining is we spent all this time to work with p3, and oh, it's in, yeah. So let me just double check and make sure. Oh, that's because originally I used this as a variable, but I never actually used it, because I was later on I created a free list to do the same thing as what I originally wanted plist to do. So that's just a leftover from that program, from that code. So now everything is good. Okay, so we'll go ahead and GDB this code. Okay, and do we want to run this code step by step, or do we want to kind of just run it all the way to the end and then figure out what it had done? You guys can tell me which way you want to go. So once again, the choices are either we run this code step by step, we stop for each iteration of the while loop, and then we try to figure out what it is trying to do, or we can just let it run all the way to line 40, then we go back and check out, okay, what is free list pointing to. So you guys get a chance to kind of tell me how you want to do this.
I think I would prefer the walkthrough method.
The walkthrough, okay. Okay, so excellent. Walkthrough it is. So we'll put a breakpoint on line 35, which is the beginning of the loop, and then we just run it. And this is the first time, okay? This is before the loop has gone through even once, okay? Because we are right at the beginning of the loop. So if I print pn, what do you think that's going to print? Well, let's go ahead and print node array first. Okay, so we'll print node array, which is an array of nodes, and it basically gives us a list or an array of nodes. So we can see the first node has a value of 0 and it has a p list of this thing here. The second node has the value being 0 and the next is null. The third one has value being 160 in decimal, and then next is this thing over here. Well, it's all uninitialized, okay? Because as an array, node array was never initialized. So this is really just based on whatever junk is left on the stack at the time. So it's just uninitialized. But what we are really interested in is not the content of node array. What we are really interested in is where is node array? Where is the beginning of the entire array? Okay, so this is more useful to us. Okay, so we'll keep track of this particular value. And now the pn is initialized on line 33 over here. We also want to know what pn is. Okay, as a pointer, what is it? And not very surprisingly, we can see that pn is pointing to the very beginning of the entire array because that's how we initialized it. Exactly. So Ramsey is correct. The first item of an array is the address of the entire array. So the address of the first item of an array is the same as uh, the beginning address of the entire array, and that kind of makes sense, right? Because it's kind of like the GPS location of the first house of a block is the GPS location of the beginning of the entire block. Okay, so are we okay with this concept? How pn got the same value as the address of the entire array. Okay, no questions about that. Excellent. Um, so now we can check the only other variable, which is free list. Okay, so we print free list, and it is null. Okay, and somebody might be thinking right now and go like, oh, but the subroutine is not going to do a single thing because it checks whether the pointer is null or not. If it will only do something if the pointer is not null. That is correct. But the question is, what pointer are we talking about? Okay, are we talking about a pointer that points to a struct node, or are we talking about a pointer that points to a pointer, another pointer that points to a struct node? It is the latter. Okay, so this is why this code looks a little bit kind of funky, because it seems like this would not work, but it does. Okay, so we're going to single step now. Single step in GDB will step into the subroutine that it's going to call. So we are now stepping into first of all the loop, and then when we single step again, it's gonna step into list shift. There we go. So we are now into list shift, and we want to know what exactly is this p list thing. Okay, it is supposed to be the address of free list, which is a local variable of main. How do we know and check that that really is the case? Okay, so once again we use backtrace as a tool. Okay, now we don't really need to use backtrace because I know exactly how we got to list shift. It's coming from main, but it doesn't hurt. Okay, so we can see that main is frame 1 from the perspective of where we are currently at in the debugger. So we can now say frame 1. So the context of GDB is now back to main, in which case I can now say, tell me where is list, what is the name of that variable again? Free list. There we go. So tell me where is free list from the perspective of main. And we can now see the address of the pointer free list ends with E008, and the parameter, the first parameter into list shift, is exactly the same because that is exactly what we're passing to list shift. We are not passing free list. We are not passing the value of free list. Instead, we are passing the address of free list into list shift. Okay. Do we have any questions about this portion, of the debug session? All right, so apparently we do not have any questions at this point. Okay, so I'm going to say frame 0, so we are now back to the context of the current subroutine. And then we single step. Okay, so the first thing um, is that going to be, are we going to go into the conditional statement? Because uh, something was initialized to null or 0, and on line 20 we are checking whether a pointer is null or not. Well, we can actually see quite clearly that plist itself is not null because the parameter plist has a non-null value. It is not a null pointer, so the condition on line 20 is going to be true. Okay, we're going to step into the then branch of the conditional statement. So when we single step, we are now getting into um, the inside or the then branch of the conditional statement, where we adjust whatever p node is pointing the next of p node of the okay, we're adjusting p next as a member of the structure that p node is pointing to whatever p list is pointing to. P list itself is for sure non-null, but what p list is pointing to can be a null. Okay, so let's double check, right? So we'll go ahead and say, what is plist pointing to? We know plist itself is not null. The question is what it is pointing. Is that a null pointer or not? And the answer is, yep, that is a null pointer. But that's okay because we are really just setting the p next member of the structure the p node is pointing to a null. Okay, and that's perfectly okay. This is how we end a linked list. Okay, is the next pointer is a null pointer. This is an indicator that the linked list has reached its end. Okay, we single step. Okay, so now we are changing whatever p list is pointing to p node. Okay, in other words, p list was pointing to a pointer that is null, and it is now going to be whatever p node is. P node is non-null. Okay, so we'll single step, and this is the end of the conditional statement in list shift, and then we basically return to the caller, which is main. At this point, it will increment pn to the next node of the array. Okay, but before we do that, let's check what is free list doing. Okay, so we say, okay, show me what is free list. So free list is pointing to a particular struct node. It was null before, which means the list uh, was empty. It is no longer empty because it's pointing to at least one struct node. Okay, there's at least one struct node in the list. But that means I'm curious. What is the struct node that it is pointing to? So the value was never initialized, so you can just forget about the value. Whatever it was would still be here. But we can see the next member, p next of that structure is now null because this is the very last item of the entire list. After we construct the list, this is going to be the very last one because the list is constructed by adding additional elements at the beginning of the list and not at the end of the list. So are we still doing okay so far with uh, analyzing, all of these pointers, which one is pointing where and which node of the array is initialized at this point? So if you have any questions, this would be a good time to ask. Let's kind of slow down and explain all of that stuff at this point. And also that gives me the time to take a sip of my coffee. No questions. Okay, so if there are no questions, we'll go ahead and run line 38. Now, line 38 doesn't seem like something that is worth mentioning, right? We are just incrementing a pointer. Well, it is worth mentioning, okay? Because when we think about increment, in most cases, we're saying, let's add 1 to something, right? That's what incrementing usually means. But when you're incrementing a pointer, you are still quote unquote adding 1, but that 1 is not the unit 1 from the perspective of the address space. That 1 is saying, let's point to the next item, okay? Which in this case is a struct node. So we are basically skipping over the number of bytes that one struct node is going to take using the plus plus pn. Okay, so the best way to illustrate this is really just to print out what is pn at this point. Single step, okay, after the plus plus pn, print pn again. And you can see that it is not incrementing at all because pn was E010, or it ends with E010 before. Now it ends with E020. Okay, it is off by 16 bytes. Okay, so this misleading auto increment is actually increasing by 16 and not by 1. So if we try to, so Thomas wrote in the text. So if we try to implement this in assembly, plus plus pm will need to use a buffer. Not exactly, it just has to skip over the number of bytes of each struct node. That's what it needs to do. So this means we probably want to check this out too, right? Because we want to check out what is the size of a struct node. And that turns out to be 16 in decimal. Wait, hold on a second here, okay? Yes. So it's basically adding 16. But now we have a big question is why does it use up 16 bytes, right? Because let's try to go back to the source code. Okay, so we'll list from line 1 because we want to look at the structure. So when we look at the structure, we say, okay, value only takes up 1 byte, and we know a pointer in the 64-bit architecture is going to use up 64 bits, which is only 8 bytes. So 1 plus 8 is 9 bytes. How do we end up with 16 over here? Padding, very good. Okay, Ramsey, wrote, padding, and that is correct. Okay, but the question is, why do we want to pad? Why are we wasting 7 bytes in this case? Alignment, very very good. Okay, we are. This is great. I like I like this discussion. So, what is alignment? What does it do? Why? What happens if we do not have alignment? So, in a 64, okay, I'll let Ramsey calculating offsets. I'm waiting for Ramsey to finish typing. And oh, okay, that's okay. No problem. So what the best way to illustrate this is to use a spreadsheet. You can see how your spreadsheets are really useful because it really is just a table. And the best way to illustrate it is to do it like this. So what we'll do is I am going to indicate locations over here. And because we are dealing with a 64-bit architecture, okay, because most PCs now are 64-bit architectures, so we'll use one column to represent 1 byte, okay. So we have 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so from column B to column I is 64 bits. Okay, and we'll use column A to indicate the address. Okay, so we'll even go ahead and use the addresses that we have been using over here. So we have 0x20, excuse me, E010. So I'm only keeping track of the least significant 4 hexadecimal digits here because it's going to be exactly the same for the first whole bunch of digits. So this is what we are tracking here. So the next one is E0218, Z018, and then E020, E028, and so on. Okay, so we look at this and then we ask, okay, so what are we talking about here? When the processor is getting content from memory, when your architecture is 64-bit, it is getting 64 bits at the same time, even if only one of those bytes out of the 8 is what you're interested in what your program is interested in. When it's reading, it's always reading 8 bytes at a time. Okay, so that means if I arrange memory like this, okay, which means the value byte is over here, and then the next pointer is all over here. So um, if I merge all the columns first, that makes it more visible. So that means the address of V or value as a member is at location E010, and then the address of the next pointer of the same node is going to be at location 18. So let's double check that, right? Because this is all the stuff that we can actually check in GDB. So we can ask, what is the address of the following thing? What following thing are we talking about? So we are talking about the node array, the first element of it, and the value member of that thing. Okay, so we're asking where is the address of the member value of the first element of the node array. Okay, that's what we're asking. And we can confirm that, okay, it is at location E010, which is also the beginning of the entire array. That kind of makes sense, okay? But when we ask what is the address of node array bracket 0 dot p next, okay, which is the next member, we can see that it is skipping 7 bytes to get to location 18 over here, which is exactly what this spreadsheet is expressing. Okay, so these two combined, okay, if I were to use a visual tool, this is basically corresponding to the first element of the entire array. Okay, this is the first node, and then these two, okay, v over here, and then p next over here. But let's go ahead and once again, merge the cells to make it obvious. So these two are basically combined. It is for the element 1 in the entire array. Okay, so is this representation doing okay so far? Is it helping to illustrate how memory is utilized when we write a program in C? Okay, so we got one confirmation, and Angel is typing. I'm gonna wait until he is finished typing. So each element is taking up 16 bytes. Each column is 1 byte. That is correct. So column B is representing 1 byte, column C is representing a byte, and so on. Okay, very good. Okay, but the real question is, aren't we wasting these 7 bytes? I mean, they are not corresponding to value. Value is only a 8-bit thing, which means it should only take up 1 byte. The answer is yes. We are absolutely wasting these 7 bytes. Okay, they are not a part of what the structure needs to represent. They're just kind of floating in memory space, not being utilized in any way. So now the question is why? Why are we wasting all of this stuff here? Okay. So let's look at what it would look like if we do not uh, waste those 7 bytes. Okay. So the question is, we are trading lookup time for this. Yes, but I'm going to explain why that is the case. And then RJ is asking, are we going to compress it or leave it? So the answer is we are leaving it like this. This is the compiler default setting is to shoot for performance and not to shoot for memory utilization. But there is a compiler switch to do this. Okay, you can tell GCC and say I want my structures to be packed, then it will go ahead and pack it. Okay, but let's look at what would happen if it was actually packed. Okay, so if it is actually packed, okay, this is the second scenario where everything is packed. Okay, then we'll say let's use up just 1 byte for V, and then we'll use the next 8 bytes for P next. So that means these 7 bytes, oops, OEM. So these 7 bytes will only be a part of P next. Okay, it's going to be let's see, the x86 architecture is a little endian processor. So these would be the first 7 bytes of the pointer, which should take up 8 bytes. So they would basically be going from bit 0 all the way to bit my math is so bad. I think it's bit 55. Okay, so we're still missing 1 byte over here. So when we move on to the next row, which is 0xe018, this 1 byte over here is going to be the most significant byte of P next. So this is actually what P next bit 56 to 63 is going to be located. Okay, so that means to make this picture more accurate, we have to kind of make column B wider just so that we can see the entire thing. Okay, so so let me use color coding in this case. So if I were to use color coding to highlight what locations in memory belong to the first element of the entire array, this is the portion. Okay, so I'm going to highlight it with kind of neon yellow for now. Okay, So now the question is, where are we going to put the next element? Right next to it, right? Because we want to utilize memory as much as efficiently as we possibly can. So V is going to use up 1 byte, okay? And now we need 8 more bytes for P next. So P next, and this time is going to go from bit 0 to, let's see how many bytes we have left here. So we only got 6 bytes left here. So it's going to be 6 times 8, which is 48, minus 1 is 47. Okay. So bit 0 to bit 47 is going to be occupying this portion here. Okay. So if I were to do a OEM, to merge those columns, that's what it's going to look like. Yes, RJ, this is going to look kind of messy, okay? But that is exactly why I need to show it, because I want you guys to understand why memory is wasted when we use the default setting of the compiler. Okay, so now we look at the leftover 16 bits of p next, the member p next of the second element of the entire array. It's going to use up these 2 bytes, right? So these 2 bytes will now be p next. I know there's a text somewhere in the. So I'm going to finish this first, and then I'll go back to the Discord chat channel to read the questions. So these 2 bytes, okay, OEM, is going to be the second. I shouldn't say second half, but these will be the most significant 2 bytes of the member p next of the second element of the array. So when would I use this kind of packing? It depends on um, a few factors. So let me highlight it first, and then I'll go answer that question. So now what you see as, I would say, salmon, okay, or orange, pale orange, um, is it would be the memory belonging to the second element of the array. Okay, so it's going to get messy. Okay, as you can probably imagine, this is going to look pretty messy because every single structure is going to take up 9 bytes exactly. So it's going to shift this thing, and then at some point it will look aligned again, and then it will misaligned again. So this type of packing is utilized if you have some kind of file structure, and the binary file structure is based on packed structure. Then you want your memory to be utilized exactly the same way, because this way you can read a binary file directly into memory space to preserve the structure. Now, something like this obviously is not going to work because pointers cannot. There's no guarantee that things will be loaded into exactly the same location, because that is kind of at the purview of the loader, of an operating system. But if you're dealing with something that's more like, just integer values, double floating point values, and strings and stuff like that, then you want to know how the data is represented in a file. If you intend to use a binary read operation to read the entire record into memory space, or read a whole bunch of records into memory space. So that is when this type of packing is useful, because you want to match how a structure is represented in memory to match how it is represented in a binary file. So Hugh has a question. So if this is how the memory is laid out, how does the memory stitch them together for processing? Well, okay, the good thing is you don't have to worry about it, okay? Because if you are trying to read, let's say, the V member of the first element, is no problem, right? Because it's just a single byte. So even though the read operation is reading 64 bits in at a time, the processor natively understands that, oh, we just need the least significant byte, and that is what we want to put into a register. So it would just basically filter out the rest and just say only this byte matters, put it into a register for some additional processing. No problem. Okay, the question is, what is going to happen if you want to read p next and say, hey, I want to dereference that address, or I want to push it on the stack. So if you're reading p next of the first element of the array, the processor will still handle it for you. Okay, so in terms of software, you don't have to do a single thing, okay, which is kind of nice. But the processor now needs to read the first 7 bytes of the address using one memory access, and then use a second memory access just to read the most significant byte of that address. This is why we use the non-packing order here, because if you did not pack, okay, then pnext only needs one single memory read operation. But once it is packed, then pnext is going to take two memory accesses. Yes, so it does take longer to read the address in this case. So Nick is commenting. So if we use so we end up using more memory when we do not pack a record, but we would have improved the access time, and that is correct. Yep. So we are sacrificing memory space for access efficiency. Very cool. Yep. So now in modern day processors, we do have caching. So when we have caching, it would the penalty is gonna be as much, okay? Because if you have to go all the way to the memory modules, to the DIMMs, the dual inline memory modules, that's going to take a long time. Okay, each memory cycle takes a very long amount of time. But because of caching and because of DDR, all the DDR technology, it doesn't really matter whether it's DDR or DDR2 or 3 or 4. They in this particular context, they work pretty much the same because we are basically prefetching stuff, and fill in blocks of the caches whenever we make a memory read operation. So the penalty is not going to be as much, because of caching and also because of the DDR technology, but it is still there because if it wasn't, then people would not be using the unpacked, format, which basically is a little bit wasteful when we are dealing with records of this kind. All right. So I know this is kind of a digression, but I want to let people understand why we are using 16 bytes per record or per structure instead of only 9 bytes per structure. And the reason is because we want to optimize for memory access. Shall we move on? Yes? Okay. All right. So apparently there are no additional questions. Oh, okay. Isaiah has. So we got a thumbs up, and we got two people typing. I'm gonna wait a little bit. Yep. Another thumbs up, and Thomas is typing. So is it only ever 8 bytes, or if p next is longer, would v take up more memory? Okay. So let me just show you something first, okay? Because I can explain it, but when you see what the compiler does, I think that will help understand this a little bit better, okay? So let's just say that value is not a single byte. Instead, it is a 9-byte thing, okay? Uh, then we'll go figure out how the compiler is going to look at this. So we go back to GDB and put a breakpoint on line 40. This time we don't really need to look at line 40 because all we're doing is to look at what is the size of one struct node. Okay, so if I were to print what is size of struct node, what do you guys think it's going to be at this point? V is no longer a single byte, it is an array of 9 bytes, and then the p next is still the same as last time. So how many bytes do you think the structure is going to be? Okay, let me read the questions here. How do you specify in the program to pack our data? So there are two ways to do it. The compiler switch is one way, and then the second way is to use what we call a pragma inside the program, inside the source code. So you can actually have some control over this stuff. Even in the source code, you can turn it on and turn it off using a compiler pragma syntax. Okay, so that kind of addresses what RJ is saying. So RJ is correct. It is a compiler setting, but there's also a pragma corresponding to this. Okay, so getting to, oh, okay, Thomas is typing. Let me ask, 16 bytes it's actually more than that, right? Because v as a member itself is going to take up 9 bytes, and then the address is going to take up another 8 bytes. So it will take at least 17 bytes to do it. So 24 bytes is correct. Okay, so let's check that. It is in fact 24 bytes. So when we look at, okay, so yep, yep, because we have to minimize access. So what we'll do is we're going to look at v first. Okay, so we're going to look at the address, okay, the address of node array bracket 0 dot v. Okay, oops, there's no member named, oh, it's value. Okay, there we go. Okay, so it is this, and then we want to look at p next. Okay, this time p next is going to be 16 bytes away from value. Okay, which is the case. Remember, these are all in hexadecimal. 10 in hexadecimal is 16 in decimal. So something that only takes up 9 bytes is now wasting or using up the space of 16 bytes, of which 7 is totally unused. Yep, yep. But this allows the processor to access memory in a more efficient way. From the software perspective, from the perspective of what you need to do, in assembly programming or in C programming, it makes almost no difference. But in terms of efficiency of accessing memory, it does make a difference. So I do want to point out what a pragma is, because I mentioned that word. Um, so we can look up GCC pragma struct pack, and I think that should find the correct pragma to do it. Structure packing pragmas using the compiler, blah blah blah, like that. So that is the case. So pound pragma sets the alignment to be the one that was in effect when the compiler started. So this is with an empty. So you can change it. You can change the alignment to a new alignment, and then it's kind of like a push and pop thing. So you can push and say, I want the alignment to change to this, and then you can pop and say, let's go back to what it used to be. So that's what a pragma is. It is something you can specify in the source code of your program and say, only for this portion of the program I want to use packing, but for the rest of the program I don't want to use packing. So that's kind of a convenient feature. But as I said, you can also use a compiler option to do it. So you can look up GCC switch structure packing, and I believe there's one way to do it too. Uh, I thought there was a switch to do it, but I'm not gonna waste too much time to talk about this because this is kind of outside of what we want to talk about in today's lecture. But there is an option to do it as a compiler switch. So do we have any other questions about the program that I just wrote? Okay, so let me get out of GDB, go back into the editor. So this way we can look at the entire program in case people want to look at it again and ask questions. So I think the node itself is not a big problem. Okay, whether it's 1 byte or 9 bytes is not a big deal. But are there any questions about the subroutine list shift, and also how we use various local variables in main? No questions? Okay, so let me just kind of go back and change value back to just a single byte. Okay, and this time we'll go ahead and recompile the program. But we'll let it run all the way to the end. Okay, so I'll put a breakpoint on line 40 and then just run it all the way to line 40. So now we'll look at list, free list, and say, what is it pointing to? Okay, we know it's a pointer, so it doesn't really help a lot if I just print the pointer itself. I want to see the structure that it points to. Okay, so this is the structure that it points to. I'm not really concerned about value because it is not initialized in any case, but I do want to look at what it is pointing to. Okay, so I want to say, so I'm going to use a very clumsy syntax first, and then we'll switch to a more compact and more conventional syntax. So this expression so far, asterisk free list, is dereferencing free list. Now, because free list has a type of as structure pointed to a structure, so this whole thing is basically a structure. And because we have a structure, we can specify, I don't need the entire structure. I just need one member of that structure. So we can now say, tell me what is the value of the p next member of the structure the free list is pointing to. Okay, that gives me a pointer, which once again is not very helpful, right? So we're going to say, let's dereference that. And once we dereference that, we can see, oh, it's pointing to another structure where the p next member of that structure is also seemingly pointing to yet another structure, right? So you can probably recognize the last four digits of the address. This is the first one. In other words, this would be the last one. So we now go back and say, let's look at the next p next of the structure of this whole thing, the whole thing that it points to. So to make sure that I think in these situations you have to use parentheses because otherwise the association or the priority of accessing a member is higher than the priority of dereferencing. So it will try to access the member before it dereferences, but in this case we want to dereference before we access a member. So you have to include that. Okay, so we access that and it is that. Okay, so that's fine. And now we want to say, what is it? You can see how we are just stashing more and more stuff on top of that. And this one has a null pointer, which is the last thing. Okay, so this particular way of expressing, I want to access a member of a structure that is pointed to by a pointer using the asterisk first to dereference and then using the dot to access a member. Even though it works, it actually makes sense, but it is very cumbersome. So the better way to do that is to say this: print free list. Tell me what is the member p list of the structure that free list is pointing to. Uh-oh. P next. Excuse me. So tell me what is the member p next of the structure that is pointed to by free list. This is the more conventional way to access that particular member in C and C++. So now, because we know this is pointing to a structure, now you can say, tell me what is the p next of that structure. Then you can say, well, this is also pointing to a structure. Tell me what is the p next of that structure. And now we get to a null. Okay, so you can chain these pointer notations, and it is naturally left associative. So in other words, it is the same thing as having parentheses organized in this particular way. So this is what we say, it is a left associative operator. All right, do we have any questions at this point? Can everybody see the nature of a linked list where free list points to a node, that node has a p next that points to another node, and that node has its own p list pointing to yet another node, and it keeps going and going, keeps going and going until the very last node has its p list being a null pointer, which basically says, I'm the last one, there's no next anymore. Can I make a quick visual of the free list? Okay, absolutely. Okay. Um, so the best way to look at this is to kind of go back to the array perspective. So we say print free list, okay, because it's printing to a node, and every node that we have in this program are members of the array node array. So we say free list, and then we say now we want to know which one of the elements are we talking to. So this should match the address of node array bracket 2, which is the last one, I think. Yep, there we go. So is that okay? This is the first item of the linked list. And then we look at the p next member of the node that free list is pointing to. It is pointing to this, which is actually the address of the second element in the array. And then we ask, what is that pointing to? What is the p next of that node pointing to? And that would be the first element of the entire array. Yes, it is backwards. It is backwards because we went through the array from index 0 to index 2, but each time we add a node to the list, it is only um, inserting the new node at the beginning of the list. So that means the last node of the array is the first item of the list. Yep, you got it, RJ. Yep, yep. Okay, so is that helping? I can't really draw pictures very conveniently, when I'm using my bigger monitor because I have to keep an eye on Discord, but I can't use the tablet feature of my laptop like I do in class. Okay, very good. Cool. So, are we ready to look at how to implement this in assembly? We got about 8 minutes left. Okay, let's go ahead and do it. Okay, so I'm gonna get out of here and I'm gonna use nvim. We'll look at alloc.c on one side. Okay, we'll do it side by side, and then we'll look at alloc.allocation.ttpasm on the other side. So this is a side by side, which I think is going to be helpful because this way we can actually see the assembly code versus the C code. And it's better than embedding the C code into the assembly code because that just gets long and sometimes it's harder to understand. All right, so first thing first, let's define the structure first. Okay, so remember when we define the structure like a struct node on the C side, that doesn't take up any memory space. Okay, because all that really is defining a template. It is not defining actually an object. So you can look at a struct like a class. Okay, all it does is to define the template of something. So the equivalence in assembly code is really just to define all the offsets from the beginning of a struct node to various members and also the size of the node itself. So the convention that I typically use is just spell out the name of the structure first and then the name of the member and then define that to be some kind of constant. Okay, so this can be 0. Well, it should be 0 because it's the first member, and then we have node underscore p next. Now I can just type 1 over here, okay, but that's not really the best way to do it. The best way is to make it relative to the previous member of the same structure. So I would do it like this, which is to some people it might be just an unnecessarily long way to expressing the same thing, but it's nice this way because if I choose to insert an additional member in between these two, I don't need to modify my code as much. Yes, we're going to need size in this case. So node underscore size is going to be the last member, which is p next, plus the size of the last member, which is only 1 byte, because in an 8-bit architecture, a pointer is only 1 byte long. So these 3 lines are defining just labels, which does not get loaded into RAM at all. So they are not in runtime, they're really only useful in assemble time. So the assembler is aware of these things, but the processor is not. Yep, we also need a no up, okay, and then jump around um, to main, okay, over here, and then we can define main all the way down here. Um, so let's also define num nodes, okay, so we'll say num nodes is just defined to be 3. The assembler is case insensitive, so even if you use all caps or you all lowercase, it's really the same thing. So let's go ahead and skip list shift for now, and we'll focus on the implementation of main. Okay, because there are some interesting stuff in main that we really should understand first before we get to uh, the other list shift. Okay. So in main, we also want to use labels to represent all the local variables. Now, because my assembler does not have a linker, so I cannot reuse names between subroutines, which means, it technically speaking, it is better off. We are better off to say, main as a prefix of my local variables. So main underscore node array is a label, and then main underscore pn is another label. Main underscore free list is another label. So now the question is, how am I going to allocate these things? Okay, free list being the last thing that we allocate on the stack should be what the stack pointer points to once we are done, decrementing the stack pointer to make room for all of the local variables. So we put a 0 here. This one being the second last is going to be relative to the last one, which is main node array. Now we have to be free list. Sorry, free list. Okay. Um, that'll still work. Okay, so we have free list here. And then we have to specify how big is free list, because now we want to specify the offset to get the PN. Free list is a pointer. It only takes up 1 byte. So now over here we have main underscore PN, and we want to know how far off is node array from PN, and it's only 1 plus, okay, because PN is another pointer to a struct node, and every pointer only takes up 1 byte. It doesn't matter what it points to, the pointer itself only takes up 1 byte. Okay, so now I have never done this before, okay, but it is important in this case, okay, because if I need to know what is the amount of space that I need to allocate for all of the local variables, let's figure that out. Okay, so I'm going to say main var local var size, okay, which is a label that represents what is the grand total of number of bytes that I need for all of the local variables. So that's really just going to be node array plus the size of node array itself. Okay, so for this, I can either wrap around the whole thing, or I can try to make the editor wider, which is still not going to be wide enough, but it's better than what we had before. So the total size of all the local variables is going to be the local variable that is the highest on the stack plus the size of itself. Okay, so we have to add to the offset node array the actual number of bytes of the entire array. So this is why we need the size, because now we need to say, okay, tell me what is the size of each node. Tell me what is the number of nodes we have. Okay, num nodes, and then multiply that. And because we are expressing values in RPN, so we are looking at the product of node size and num nodes. That tells us how many bytes the array is using, but it doesn't add to the offset of the array. So now we append a plus over here. So when the parser goes through this, what it is going to do is looking at this number and go like, okay, let's save it on the stack. It looks at this number and say, now save it on the stack, and look at this number and say, let's put it on the stack as well. But when it sees the asterisk, which is the multiplication operator, it will pop the last 2 items from the stack, perform the multiplication, and then push the product back onto the stack. So that means by the time we encounter the plus symbol, we would have only 2 items on the stack. The first one being the node array, the offset to node array, and then the second one is the product of node size and num nodes. So when we look at the entire thing, this entire expression, that will tell us how many bytes we actually need on the stack for all the local variables that we have allocated. Is that okay? Are we getting this part here? Okay, very good. So with all of these labels defined, we'll first initialize the stack pointer, which is sub dd. Okay, that's just for initializing the stack pointer. And then what we'll do is um, we'll just do LDIA with main local var size, and then we'll do a subtraction dA, and this is for allocating for all the local variables. Okay. So now at this point the labels are relevant. Okay, so all the labels that we have defined over here, they are now the correct offset from where the stack pointer points to. So I can make a note about that. Okay, so at this point all the offsets to local variables are correct. Okay, so now what do we do? Well, we have to do some initialization. In C, it is copying node array to Pn. It is really copying. It's not copying the array to Pn. It doesn't make sense, right? Because the array is taking up a lot of bytes, and Pn as a pointer is only taking up 1 byte. So this is really implicitly saying, let's use the address of the array and then copy the address of the array to the pointer Pn. Okay, so this is really kind of important to understand that in C and C++, you cannot copy an array by value. When you specify an array, you're only specifying the address of the array and not the content of the array. Okay? So we'll use our typical structure of code, which is LDI A. Any register A, B, or C is fine, and then we specify the offset, which is main underscore node array, add AD. Okay, so at this point A is really the address of the array, which is what we can stop. Okay, we do not want another LD instruction here, because if I do LDAA, okay, then A becomes the first byte of the entire array, which is also the member value of the first element of the array, which is not what we want. Okay, we just want the address. So that's why we have to stop here and not to perform another dereference. We are not looking at the content of the array in any way. We just want to access the address of the array. So now we use a similar technique to calculate the left-hand side, which is Pn. So we say LDIB with main underscore Pn, and then add BD. So that B is now the address of Pn. And then we have a single store instruction so that we accomplish dereferencing the address of Pn, and we change that location to whatever A has, but A has the address of node array, and therefore now we accomplish the first line in C code. Do we have any questions about this one? No questions? Yeah, so I know we are going to be running a little bit over time as well, okay, but I think it's important to at least finish main. We can forget about the function call and leave it to next Tuesday to go over, but I think it's important to just finish main at this point, because otherwise we will lose the context of all of this stuff. So we'll go ahead and finish that first. So I'm gonna work a little bit faster now. Okay. So that would initialize the free pointer. And now onto the while statement. Now, when you're dealing with a while statement, um, this particular while statement is interesting. So we'll first create the structure of a usual while statement. So we'll say while begin, and before we get to the end, we have an unconditional branch back to while begin, and then at the very end, okay, after this we have while end to mark the end of the array. So of the loop. So now we can now specify the condition of the loop over here. It looks simple, but it's not really as simple as it seems. Okay, because we are definitely comparing pn. Okay, so we can load pn into a register first. Okay, so we say ldia main pn add ad, and then this time we do need to dereference it because we need a to be pn and not the address of pn. Okay, so we need a load to do that. So that will be the left hand side of the comparison, or one of the items that we need to compare. So now the question is, what is this saying? Node array plus num nodes. That really is asking what is the address of the of a node that is beyond node array. Okay, so this is interesting in many ways. Okay, so the first one is how do we calculate that? Okay, so we'll first deal with that question. So it is main underscore node array, and then we say add ad. So at this point, a is now the oops, not a, it is b. So at this point, register b is the address of node array. Okay, which is something that we did already when we were working on the first line in C code. So what is the plus num nodes doing? That actually is adding um, not just num nodes, but num nodes times the size of each node. Okay, so if I want to do it in a very clumsy and long way, I can do it like this. Okay, and I will talk about how to do it in a not so long and clumsy way later. So we'll basically look at num nodes, um, and then we have node underscore size times, and then we add this to b. Okay, so what this really is doing is we want b to end up with the address of node array open bracket num nodes. If I were to write this in C, this is what we have accomplished, and that actually is the meaning of the right hand side of the comparison operation. Okay, so now first thing first, okay, I mentioned this is kind of clumsy and I used the wrong register in the add instruction, so it's supposed to be C over here. So this is the clumsy way to do it, because if you think about it, this expression, whatever I'm loading into register C, can be statically calculated at compile time or at assemble time. So that means I can fold the calculation based on constants into one single calculation all the way up here. So I can actually specify this and a plus all the way up there and not need these two anymore. Okay, so this looks a little bit awkward, but it does work, okay, because we can fold all the calculations involving only constants into one single calculation. As long as we don't need anything at runtime and they can all be calculated at assemble time, we can do all of that. We can fold all of that, at assemble time, and that helps to save some instructions and execution time. But the second problem of this is we are now specifying a number that turns out to be just 0, because this is the one byte past the end of node array, and node array being the first local variable to be allocated is right at the top of the stack. So that means one byte past the end of this is going to be at location 0. And so we have a little bit of an issue is when we compare two pointers, we're going to use the compare instruction. And what is going to happen when we use a compare instruction in this case? So now we want a compare instruction, and to stay in the loop, we want register A to be less than register B. So that means if I flip the comparison and compare BA, then I can go when they are the same, or we can go when one is not less than the other one. Okay, so that means we can have a JZI to while end, and then we also have a second branch instruction. Technically, we need to have a JCI because it's an unsigned comparison because pointers are not signed. Also to go to while end. Okay, and this is going to be a problem. Okay, this is going to be a problem because guess what? B is going to be 0, and 0 is less than um, 0 is less than all unsigned integers except for 0 itself. So that means between these two JZI instructions, one is going to fire anyway. Okay, so JZI is going to fire or JCI is going to fire if A is non-zero. So we have a problem because because of the way I structure the stack, this is a problem. Does everybody understand why we have a little bit of an issue here? Okay, no one. All right, so the fix to this problem, and they are both highlighted as incorrect. I think it's because my syntax rule is not entirely correct, so I have to fix that too, but they are actually correct at this point. So I'm going to have to get rid of the second one. In other words, I'm just going to comment out this one because it is not going to work. Okay, not going to work because register B is going to be 0. Okay, all right. So given that this is how we're going to structure the condition of the loop, we're not going to make the call for today. We just want to go through the array using pn. So we're going to implement just plus plus pn at this point. That would be the end of what we're going to do today. So what are we going to do with this? Okay, we kind of know how to increment something. We need to get to it and then change it and then store it back. Okay, so we kind of know how to do that. So we have to do a LDI with a register, main underscore pn, add ad. So now a is the address of pn. Then we have to load it into a register, not a, because we want to keep a around for a little bit. And then we increment b, and then we store that back to whatever a is pointing to. Okay, and that's the usual way of doing increment, but not this time. Okay, the reason why this is not going to work in this case is the increment, that what seems like an increment or increase by 1 in C is not really increasing by 1 in assembly, because the so-called increase by 1 in C is changing the pointer to point to the next node. Okay, but in order to point to the next node, the number of bytes we have to skip has to do with the size of node. So even though it looks like just increasing by 1 in C, in assembly it is not quite that simple. So in assembly, now we actually need to utilize the third register, which is register C. And then we have to use node underscore size for this one. And then we add C to B, and then we store B back into whatever A is pointing to because A is still the address of Pn. So this is how we advance Pn, and say for each iteration we're going to quote unquote process the node that Pn is pointing to, but we are not implementing the function call, so that's not actually happening. And then the post operation, which is plus plus pn in C, is implemented by adding node size to the pointer itself, because we are basically trying to skip over to the next available structure. Okay, so are we still doing okay so far with this code? Increment b node size does not work, okay, because increment can only take one single register. So if I were to try, so in concept, yes. Okay, so in concept, yes, but we cannot do that because if I try to do an increment b node underscore size. This time the syntax highlighting is actually correct. It doesn't work. Okay, this is one where I have to fix it some later on, but this one actually does not work. Okay, the assembler would actually complain about this. All right. All right, so I think it's probably a good thing to actually run this code and see that it completes, and then we can conclude this lecture. Okay, because I do want to run this code to show you how it's going through every single element in the array. Okay. So we'll go ahead and specify a halt instruction here, because that's really the last thing we want to do. And then before that, to balance the stack, we're going to say LDI A with main underscore local var size. And then this time we are adding that much to the stack pointer to deallocate all the local variables in main. Okay, so now we save it. I also learned this new trick today, which is percent, which selects, basically it's the same thing as select all, and then we oops, nope, I take it back. It is just W. Okay, W is normally writing the file, but this time we specify something like this. This space is important, so it's W space and then the exclamation point. Then we can specify a command in Linux, so that we are basically piping the content of the file to whatever command I specify after the exclamation point, which is xclip-sel clip here. So this is allowing me to take the entire content of the file and then put it into the clipboard. Okay, which allows me to go to the assembler and paste it in the assembler. Okay, so Bo has a question. I'm gonna keep an eye on the question. Can we get a copy of the assembly code? Yes, we can definitely do that, but let me make sure it works first. Okay, so that's a great idea, but I don't want to give you guys faulty code. So we'll go here and paste. Um, so this is RC2 of the new assembler. If you feel that that may that may still have bugs and don't want to use it, I can totally understand it and don't use it. But I'm personally trying to use this as much as possible to kind of help find issues. And so we have a problem with, oh, okay, it's node instead of node size. No, there's node size. Okay, I think that's just a typo on my part. Um, let's see. I'm gonna fix the source code first, so this way we don't. Okay, so it's on this line. Okay, node array, and then we have node size. Yeah, so pretty sure that's just a typo. Okay, I'm just double checking to make sure. Okay, we do need a node num nodes here. Okay, so it's num nodes instead of the other one. So num nodes times node size, and then the product added to node array is what we want. There we go. Okay, so we'll do the whole thing again, or we can just go ahead and change the spreadsheet. Yeah, so I think I'm just gonna go change the spreadsheet here. So it's not node, it is num node, and I think it's plural num nodes. And interestingly, it's not triggering a recalculation. So that means I'm gonna have to go here and make a non-essential change and see if that triggers. Yep, that triggers the reassembling. And it still thinks it is no node. It's not changing that because the value did not change. So I'm gonna have to change this to 4. So that is interesting. Mm. All right, so let's go back to the other assembler. Alright, so this time we'll just copy from here and paste. And there's no error this time. Very good. Go to RAM file. And go to the, oops, go to the command line. Let's double check it's actually here. Yep, okay. So we need to look up the previous Java command, which is not the one that we want. Okay, this is going to be allocation. And I go back to the trace analyzer. And we are going to import from the log file. Alright, so when this is happening, I'm going to explain how we are going to check whether the program works or not. We go to the source file first, and then what we'll do is we're trying to figure out where is PN, because PN is the only thing that is changing in the loop, so we want to figure out where that thing is. Num nodes is 3, so we know that this is starting at location basically 100 in hexadecimal minus 3 times the size of each item, which is only 2. So it is F, basically it's 00 minus 6. So that should give us FA. So the start address of main is FA, and that means PN, the pointer itself, has an address of F9. So the location F9 should basically go from FA to FC to FE and then to 00, and then the loop should conclude, and then we get to the then we deallocate the local variables, and then we hit the halt instruction. So that's what we should be looking for in the trace, is location F9 getting changed 4 times. Okay, the first time is the initialization. It's just initialized to FA. Then it should change 3 times after that to FC, FE, and then back to 00. Okay, so let's go to the trace and see whether that is happening or not. And we can use column C to help us, because column C is reflecting changes to RAM locations. So we'll just go ahead and scan it for, okay, so this is the initialization. As I said a little bit earlier, F9 getting the location F9 getting the content of FA is how we initialize PN. And then after this, it should have 3 additional updates. The first one is to FE, oh, FC, because FA then FC, and then to FE. And then the last update should update to 00, and then at which point we should exit the loop. Okay, so after this update, it goes back to the beginning of the loop, and then it evaluates and checks for the condition. And then we should see the Z flag setting after the compare, which is happening right there. Then it should exit the loop, So it went from 1C to 2.8. That's how we exited the loop. And after we exited the loop, we adjust the stack pointer to deallocate all the local variables, and then we hit the halt instruction at the very end, and the program stopped. So this whole thing works exactly the way I described it, which is really surprising because there are so many things that could have gone wrong when I wrote this code. Um, so anyway, I am going to post this and pin it to today's channel, text channel, so that you guys can look at both the C code and also the assembly code. Once you have the assembly code, you can basically run it on your own. So you can run it on the command line and use the trace analyzer to analyze it, or you can just make a copy of the trace analyzer right now to capture the actual trace of the code. So it's up to you guys to decide how you want to do it. So that should technically end today's lecture, but I'm going to um, leave the voice channel open until I have posted the files, and then I'll keep an eye on the text channel to answer any questions that anyone might have, and type it in text. And have a nice weekend. All right, so I think I'm just going to zip both files, and then I can just upload one single zip file. All right, so it's all done. I'm going to turn off this